Hello everyone, this is the first of 4 videos taking you through the Work, Energy and Power chapter in Further Mechanics 1, which is actually chapter 2. So a lot of this chapter will be revising a lot of your knowledge from GCSE science as well. This first section we're going to look at a few examples and we're just concentrating on the work done by a force. So just to remind you, the work done by a force is the component of the force in the direction of motion multiplied by the distance moved in the direction of the force. We'll come on to this component of force idea in examples 4 and 5, but the first couple of examples are fairly straightforward. So moving straight on to example number 1, we've got a box is pulled 7 meters, so a distance of 7 meters, by a horizontal force of 15 newtons. So quite simply here we've got the work done is the force times by the distance in the direction of the force. So it is simply 15 multiplied by 7, which gives us 105 joules, which is our unit of work done and energy. Now, example number 2 is fairly similar, but this time we've got a packing case is pulled across a horizontal floor by a horizontal rope. The case moves at a constant speed so the acceleration is going to be 0, and the horizontal force is, well, we'll give as F, and it's told that there is a constant resistive force of R, so resistive force opposing the motion. Now in this case we're told that the work done is 96 joules, and it's a distance of 12 meters is the journey across the horizontal floor. So with a simple bit of rearranging, this time we've got 96 is going to equal F times by 12. Therefore, F is going to be 96 divided by 12, giving us a driving force of 8 newtons. Now, from your normal maths work, you'll recognise equations of motion, or obviously because the acceleration is 0, therefore we know these forces are in equilibrium. So we can say straight away that R equals 8 newtons too, or if perhaps you hadn't spotted that, you could still do an equation of motion. So F equals ma in the direction of motion, and you would have F minus R equals 0. That's at the point perhaps when you'd realise that the acceleration was 0. So as we've said already, therefore R is equal to F, which is also equal to 8 newtons. Now example number 3, we are looking at a vertical motion question. So this time we've got a bricklayer raises a load of bricks of total mass 30 kilograms. So we can model that as a particle where our weight is obviously going to be 30 lots of G. And just remembering that we take G to be 9.8 throughout the mathematics module, so 9.8 meters per second squared, which can also be written as ms to the minus 2, of course. So there is our weight, and it's pulled up by a constant speed attached to a cable to the brick. So we'll call that T for tension as it's a cable, and again we have a constant speed, so our acceleration is 0. So in this case we've got work done in raising the bricks was going to be the force, so tension in this example times by the distance, which was a distance of 7 meters. So the tension here, again, because our forces are in equilibrium, because the acceleration is 0, we therefore know that T is going to equal 30G. So our work done is going to equal 30G for T there, multiplied by 7. So 30 times 9.8 times by 7, and that gives us an answer of 2058. Now it's important to note that nothing in the question was given us to more than 1 or possibly 2 significant figures, so it's appropriate to leave our answer to 2 significant figures, so that will be 2100 joules. Now as I said, this component of force in the direction of motion I said I would come to. So example number 4, we have a package being pulled up an inclined plane. So in this case we've got the mass of the package as 2 kilograms, so straight away we have a weight of 2g. It's pulled at a constant speed again, so our acceleration is again 0, up a rough plane which is inclined at 30 degrees to the horizontal. Now the reaction force is always at right angles to the surface, and because we have motion we know the friction force must be at its maximum. So you may remember that F max is mu times R, where mu is the coefficient of friction, and in this case we're told that the coefficient of friction is 0.35, so we can say that that's 0.35 multiplied by R. And again, our driving force that's pulling it up the plane. Now it's pulled a total distance of 12 meters. So if we're looking at work done by gravity, well, the gravitational force is going to be 2g multiplied by h. Now, just as a point that we're going to be looking at in the next couple of videos, you'll probably recognize that gravitational potential energy is mgh, and you'll see the similarities here, because obviously the gravitational potential energy is the work done by our gravitational force. So the thing here to bear in mind is that the distance in the direction of the force is obviously not going to be 12 meters. It's going to be the component of 12 meters vertically. So because we've got 12 meters and the inclined plane is 30 degrees, we therefore can say that h in this case is going to equal 12 sine 30 degrees, which is obviously going to be 6 meters. So our work done by gravity is going to be 2g times by 6. Again, the direction of the force, the distance travelled there, is the 6 meters, and we therefore get that our answer is going to be 117.6 joules. And again, because we were given things to only 2 significant figures, it's more appropriate to write that as 2 or 3 significant figures, no further detail. Now, the work done by friction is slightly more straightforward in the sense that the direction of the force is the same as the direction of the motion. So our work done in this case by the friction is simply going to be 0.35 R, which is our friction force, and that will be multiplied by 12. So to be able to find out what R is, we need to resolve perpendicularly to the plane, I mean to say. So here, some people are happy to write our weight there in 2 components, or you can see that the 30 degrees would fit there. So you'll hopefully see that the component in that direction is going to be 2g cos 30. So therefore we know R is going to be equal to 2g cos 30 degrees, and therefore our work done by friction is going to equal 0.35 times by R, which is 2g cos 30 degrees, and that's multiplied by the distance. And as we said again, the distance is in the direction of the force, so it is the full 12 meters. And that gives us an answer of 71.29, etc. joules. And again, to 3 significant figures, that would be 71.3 joules. Now, the final question is actually quite a bit simpler, but it does emphasize the point again of our component of the force in the direction of motion. So the final example, we have a sledge, if I just sketch it very quickly there, is pulled 15 meters. So it's pulled a distance of 15 meters across a smooth sheet of ice by a force of magnitude 27 newtons, but this time it is at an angle of 25 degrees to the horizontal. So here, to find the work done, we need to find the component of the force in the direction of motion. So again, from your normal maths work, you will know that you can resolve our force into 2 components. That would be 27 sine 25 degrees, and this component 27 cos 25 degrees. So in this case, the work done by the force is the component of it in the direction of motion, which will be 27 cos 25, and that is multiplied by the distance travelled, which this case is 15 meters. So 27 cos 25 multiplied by 15 is going to equal 367 joules. So you've now gone through the examples that you need for exercise 2A, and the next video we will be moving on to energy. So good luck with those questions, and I'll see you in video 2.